So this section is on Newton's method, and you'll notice that the notes are relatively short, just the front and the back of one piece of paper. And what we're going to start off by doing is we're going to start off by solving this equation right here. And there are many times in math where we take advantage of what we call the zero property of multiplication. So when you first learned how to solve something like this, you certainly we wouldn't be solving this by taking a square root, even though there's an x squared there. We're going to move everything onto one side. So we're going to make this x squared plus 3x plus 2 equals 0. And there are a whole bunch of addition problems that have an answer that equals 0. But if you write this as a multiplication problem, the only way you can have a 0 in a multiplication problem is if there's a 0 in there, a 0 for a factor. So we're going to factor this. We're looking for two numbers that are going to multiply to be positive 3 that add up to, multiply to be 2 that add up to be 3. So that's going to be positive 2 and positive 1. And then we take each one of those independently and we set each one equal to 0. And then solve each one of those pieces. So I get x equals negative 1 here, and I get x equals negative 2 here. Okay? And finding x-intercepts is a really important skill. Finding where a graph crosses the x-axis is very useful. So there have been a lot of mathematicians that have spent tons of time trying to come up with ways to find x-intercepts. Now, these numbers happen to be really nice. Okay? If they're not very nice, then usually we end up relying on a calculator to do that. But it turns out if we use a little bit of stuff that we already know how to do and a little bit of calculus, we can actually find really ugly, maybe even irrational zeros of a polynomial or zeros of a function, x-intercepts of a function, okay, using this idea. So what we're going to start with is we're going to start by finding the x-intercept for a linear function, but we're going to do it in kind of a strange way, okay? So if I were going to solve this, and I want to know what x is, I want to know when this, what I plug in to make this function right here equals 0. First thing I'd do is I'd move the 8 to the other side. So I'm going to subtract 8 from both sides. That's going to give me negative 8 equals 2, and then x minus 3. I'm going to get rid of the 2 by dividing by 2, only I'm going to leave it in this format. I'm going to leave this as negative 8 over 2, and over here I have an x minus 3. Okay, then I just take the 3 and move it to the other side by adding, so here's what I end up with. I end up with x equals 3 minus 8 over 2. I mean, if we did the math, that gives us x equals negative 1, right? Okay, but let's look at a picture of what we just did, and let's see if we can match some stuff up here. So this is a picture of a line whose slope is 2 that goes through the point 3, 8. So if you'll notice, this is like the format where we had y equals mx minus x1 and then plus y1. It's that same type of format. And what we can do is we can just kind of take that point and we can follow this line using the slope and figure out where it crosses right here. Okay? So if the point is 3, 8 and the slope is 2, then the root, the x-intercept of that line is going to be that old y value. Whoops, that old x value. Old x value. And then minus the y value, which is 8 over 2. So here's the old x value. Okay, we were sitting here, right here at 3. The y coordinate is 8, and the slope is 2. So if we go to this point on the line and just, again, follow that slope down here, it's going to show us where it crosses the x-axis. So if we were to think in terms of calculus and we were to kind of generalize this idea, well, this point could be located, we'd call that A. So the x-coordinate is going to be A. The y-coordinate is going to be f of A. And then we'd call the slope the derivative at that point. So the derivative in this case is going to be 2. So in terms of the numbers in this problem, it would be the old x-coordinate. Okay. This is the old y-coordinate. and this right here is the slope. Well, if we generalize this and thought about this in terms of calculus, here's what we've got. Okay, the root or the x-intercept for a linear equation is going to be, well, let's see, let's stick with this right here. Let's stick with a. The old x-coordinate is a. The old function value is f of a, and then the derivative at that point is f prime at a. So if you've got these three quantities, you can figure out where your line crosses the x-axis. You need the old x-coordinate, you need the old y-coordinate, and you need what the slope is. And again, we can just kind of follow that down, and it shows us where it crosses the x-axis. So in order to use this method, we need the x-coordinate, we need the function value at that x-coordinate, and we need the derivative at that x-coordinate. Okay, now that's just for a line. That works for a line. Okay, but what Newton noticed is that, well, you can take any curve and you can find the tangent line. So let's take a look at what he was looking at. So what he realized is, let's say this is the root that we're after. We want to find where this curve crosses the x-axis. It crosses right here. So what we do is we take a guess. And we take a guess and we say, well, we're pretty close. We think this is about 0.5 or whatever it happens to be. We take a guess that's pretty close. And then we find a tangent line for that curve. Well, once we've turned that curve into a tangent line, it's pretty darn easy to find the x-intercept or the root of a tangent line, of a linear equation. So if I take this guess, come up here and make a line, I follow that straight back, and I end up with that right there. Now you'll notice that this guess, this root, is a little bit closer than this one right here. So if we initially guessed this one, the tangent line, if we follow that straight back, it's going to get closer to the actual root than what our original guess was. Okay? And again, the cool part about our guess right here. And x of n plus 1, that's going to be the next guess. And it's written in terms of those three things. What's the old x-coordinate? What's the function value at the old x-coordinate? And what's the derivative at that old x-coordinate? Just those three things will find a better approximation for the zero or the root or the x-intercept or whatever word you want to use. Okay? So what Newton noticed is, well, if it works once, why couldn't we use it again and again and again? So here's the idea. Here's our first guess. So our first guess, we're going to use x naught, x sub 0. So there's our initial guess. We come up here and we can find that x-coordinate, that y-coordinate, that function value, and we can find the derivative there, and we can follow that down, and this will be our next guess. So if this is x naught, this is x1. This is our next guess in line. Okay, remember this notation with subscripts, and they're called indices when you dealt with sequences and series in 1050. Okay, we'll talk a little bit more about that in just a second. Well, then we'll do the process again. We'll take this x-coordinate, this new guess, find that point on the curve, so x1 comma f of x1. Find the slope of that line, so find that tangent line and follow that back, and that's going to be our next guess. So we went from our initial guess, our next guess, our next guess, and then we continue doing that, and what happens is we get closer and closer and closer to that zero. And what's amazing is how quickly this happens and how accurate it can be. Now, you can't use a graphing calculator in this class, but you can use a regular old scientific one, and I'll show you how you can do this. Get really, really accurate answers very quickly, and even how we can do a couple iterations by hand, and we'll find a really accurate answer. So here's the way we do this. We're going to make an educated guess. So we're going to look at a problem, and we're going to say, I think that crosses at around 1. And that's going to be our initial guess. So we're going to make a guess as to what the root is. Okay, and then we're going to use this formula right here. X sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So let's talk about what each one of these things is so we're sure that we can get this right. Okay? Okay. So this right here is our old guess. This is the function value at our old guess as to what the x-intercept is. This is the derivative at the old guess, at the old x-coordinate. Okay, in other words, that's our slope. Okay, and if x sub n is our old guess, this is going to be our new guess. So this nice little compact formula here says, look, if you give me an old guess, I can just plug these into this little formula and it's going to tell you what a new guess is. And then you can just repeat the process over and over again. So again, x sub n is our old guess, and x sub n plus 1 is our kind of our next guess in line, okay? Our new guess based on the old guess. So this is kind of like a recursive definition of how we're going to find these. So let's solve a problem. Go ahead and flip the page over. Okay, that's a picture of what this looks like. And I realize everybody in here can solve this equation. You know exactly when this equals 0. There's one point right here and one point right here where this crosses the x-axis. They are at plus or minus radical 3. Okay, so the answer to this is going to be radical 3, which you can type in your calculator and you can get a big long decimal approximation for it. We're going to find this answer pretty darn quickly, or get some good approximations by hand using Newton's method. Okay? So again, that formula is x sub n plus 1. So our next guess, our new guess, is based on our old guess minus the function value at our old guess divided by the derivative at our old guess. So we're going to have to make a first guess. So our first guess, if you want 2, that's great. If you want 1, that's great. It's somewhere in between there. Let's go ahead and guess 2. So this is going to be x naught. There's our guess. There's our initial guess. Now, in order to make this calculation, I'm going to need to figure out what the function is. I need a function, and I need a derivative of that function. Well, the function is just what we're working with here, what we've set equal to 0. So that's just going to be x squared minus 3. And the derivative is just the derivative of that function, so this is just going to be 2x. So the way I like to do these is I just like to circle this one. Here's my first guess. There's my initial guess. Okay, now my next guess, if I plug in a 0 here and a 0 there and a 0 there, so x sub 0, x sub 0, x sub 0, x naught in each one of those, that means the index n is 0. That means I put a 0 right there. So this would be x sub 0 plus 1, so that's just going to be x sub 1, right? So I've got x naught. The next one in line is x1. It's based on the old guess of 2 minus the function value at the old guess. So let's plug in a 2 into the function. 2 squared minus 3, we end up with 1. And then I need the derivative at that old guess. So that's going to be the first derivative evaluated at 2, so that's going to be a 4, right? So what do we get? Okay, we get 7/4. We get 1 3/4. We get 1.75. Okay, now I'm going to leave it like this right here. So I'm going to say my next guess is 7/4. Let me circle that. Okay. I suppose it's possible. This is in the course. They could ask you to do this on a final exam, and they'd usually want to see a couple of iterations by hand. The worse the numbers are, we plugged in a whole number. That wasn't that bad, but now we've got to plug in a fraction. Okay, let's go ahead and run through the math with one iteration, and then I'll show you how you can do this on your calculator. We'll do at least one more by hand. So this next guess is going to be based on the previous guess, 7/4, minus the function value at that old guess. So that's going to be, let's see, 7/4 squared minus 3. So let's see, 49/16 minus 3, so that's going to be in 16ths, that's 48/16. So that means the numerator is only 1/16. And then the denominator is going to be 2 times this guy right here, so that's going to be, okay, 7/2. I mean, ugly, but still doable, right? So this is going to be 7/4 minus 1/16 times, flip that over and multiply, so that's going to be 2/7. Good there? Cancel here. So I get 7/4 minus, this is 1/56. That doesn't look like fun. Let's see. So now I need to get a common denominator. So let's see. I've got to multiply by 14, right? Okay, so this is going to be, correct me if I'm wrong, but that's 98/56 minus 1/56. Is that right? Fourteen times 7 would be 70 plus 28, so 98/56. So we end up with 97/56. So x2 is 97/56. Okay, now, we were finding this one right here. This one right here is radical 3, right? So radical 3, if you type that into your calculator, is approximately what? 1.732. Give me a couple more. 0.5. 1.73205. That's on the calculator, right? Okay. 2 is kind of close. I mean, we did a decent guess. That was within about a quarter. Okay, about 0.27. Okay, this is 1.75. That's within 200ths. Okay, type 97/56 into your calculator. 1.73214. Okay, that is within, what are we? Within a 10,000th? Yeah. It would. We're going to do that right now. Okay. Not by hand, thankfully. Not by hand, thankfully. Okay? Okay. So here's what we're going to do. Okay. On your calculator, if you type in, so I'm going to do this as if you've got like a TI, and if you could use a graphing calculator, there's some really cool things where you could shorten this up a bit, but they don't let you use a graphing calculator. So here's a way you can get around it with a regular scientific calculator. Okay, so the first thing we're going to do is we're going to clear off the screen. Okay, and if you've got one of these TI 30s or 34s or something like that, it's going to look very similar to this. Okay, our initial guess was 2. So type in a 2 and hit enter. What that does is it stores into the calculator. It says, well, that's the last answer that I have. That puts it in the calculator's memory. Okay, and then we're going to do this. Remember, the method is based on what our old guess was. We just put in our old guess, and in these calculators, it's stored as the answer. So we're going to do answer, function of the old answer, and then the derivative of the old answer. So let me show you how that's done on this problem right here. Yeah, you can do this on the TI-30. Okay. So let me write down what the function is so we can see it over here. So f of x is x squared minus 3, and f prime of x is 2x. So when we type this into the calculator, here's what it's going to look like. I'm going to grab answer, okay, second negative or second ANS, okay, and then minus, and then I'm going to start a set of parentheses, and I type the function with that word in it. So the function is whatever that answer was squared minus 3. So I'm going to do answer, answer squared, get it right, minus 3, close the parentheses. That's going to give us the function value on the top. And then I'm going to divide by whatever the derivative was, and it's a good idea to put these in parentheses even if it doesn't look like it's necessary. 2 times whatever that last answer was, whatever that last x value was. Okay? So here's our old guess. Here's the function value evaluated at our old guess. Okay, and here's the derivative evaluated at our old guess. Okay, in this case, instead of old guess or x naught or xn, we're just plugging in answer. Okay, now, if this is in there correctly, what should our first iteration tell us? What was our, should be 1.75. Okay. Now, you can just hit enter again. I'm not sure if you can do that on these calculators, or you can just hit the up arrow and grab that command again and hit it again. We should get this ugly thing right here. Looks right. We can also, I haven't done this before, but these calculators do have the capability to change things into a fraction. So I'm going to take that last answer and change it into a fraction. There it is, 9756 right there. Okay. I'm going to recall that other command where we're using Newton's method. Old guess minus function value at old guess divided by derivative at old guess. Just taking that point and following the slope right down to see where it crosses the x-axis. What's that? I hit second enter. Second enter a couple times. On those, you can just hit the up arrow on a TI-30. Okay? So what are we looking for again? Okay, I wrote it out to 5 decimal places. This is the third iteration. And we're already accurate out to here. Now, if I hit it once more, it changes a little bit. And then it's not changing at all. Now, this was the third one. This is the fourth one, right? And it's not going to change again. Why is it not going to change again? Because it's right there. It's right on it. Okay? So just for the heck of it, like Juan suggests, I'm going to put in a radical 3. And there it is right there. Okay? 4 iterations. And we've got the answer accurate out to 9, 10 decimal places. Okay? Pretty amazing.
Is it always the fourth time?
It's not always the fourth. What would it depend on? Good question. How close your guess was. It's going to depend on the slope. Okay? And we'll look at a diagram in just a minute that'll show us a couple of other things. So let me show you how to do this again. On some of these, it really would be possible to only do maybe 1 iteration by hand. You're going to need the help of your calculator in some way. Okay, whether it's to evaluate the functions and you're keeping track of decimals or fractions or something like that, or having your calculator do what I showed you there. Okay, honestly, on a test, I'd want to see maybe 1 or 2 iterations by hand, and then I'd want to see you use a calculator. Okay, it would be crazy to do this more than once or twice without the use of a calculator. Okay. Plus, it makes it just a lot more fun. Okay? All right. So let's take a look at example 3. This first one, again, it's got a trig function. If you're using a calculator that has different modes on it, you definitely want to make sure that we're in radian mode. Okay? Because we'd have to find a real number where it crosses the x-axis. So the first thing we notice about this is it's not set equal to 0. You've got to set this equal to 0 so that we're finding the x-intercept. Okay? So I'm going to move this stuff over to the other side. So this is going to be 3 cosine of x minus x plus 1 equals 0. This right here is f of x. So our function on this one is 3 cosine x minus x plus 1. We need our derivative. So our derivative is going to be negative 3 sine of x minus 1. Need a function value, need a derivative at that function value, and I need an initial guess as to where this crosses the x-axis. So you could cheat and use a graphing calculator and take a look at where it crosses. Okay, or you could stop and think about this for just a second. This is a line, yeah.
Could your guess be any number?
It could, but we want to get as close as we can.
Yeah,
okay. Okay. So this right here is a line that crosses at 1 and has a slope of negative 1. And then we've added this cosine curve to it. So what we get is a wavy line like that. Okay. Happens to vary from this by up to 3 units because the amplitude of that is 3. And they actually took this section out of the trigonometry course. It's in section, what is it, 2.5, I think, in the trig book that they use, okay, where you actually combine functions. This is a wavy line that goes down from left to right, okay? So if we had to take a guess, question? No, we're going to guess slower on this one. Okay. Okay. So if it crosses at 1, so if you put in a 1, let's see, we get a 1 out of this one, we get a 4 out of this one, so it actually crosses up here at 4 and then it heads down. So I wouldn't guess 0, I'd maybe guess something like 1. Okay, now if you throw that into your calculator, and again, on the test, if I give you something like this, I'd give you one where you can kind of tell. Like on this one, I mean, you know what that graph looks like. Okay, this one's a little bit unfair, but this one would be fair game. I'll show you that one in just a second. Okay, so let's make our initial guess. Let's make it 1. We know it's going to be positive, so let's guess an easy positive number. So that means the next one is going to be 1 minus 3 cosine of 1 minus 1 plus 1 divided by negative 3 sine of 1 minus 1. One's not a radian angle that I know the sine of or the cosine of, so we're going to be using a calculator on this one. So again, here's the idea. I'll clear the screen off. I'm going to put in my first guess. My first guess is a 1, and I hit enter. Again, that stores that in the answer. Okay, and then I'm going to say, well, my new guess, my new root, that's hopefully going to be closer to the actual root of this function, is going to be the old one minus, and then I start a set of parentheses. I have to evaluate the original function at the old guess. So that's going to be 3 cosine, whoops, and I better make sure, yep, I'm in radian mode. Okay, 3 cosine of that old answer minus that old answer, and then plus 1. I'll close the set of parentheses. Divided by, start a set of parentheses because we've got to evaluate this function here, negative 3 sine of that last answer, close the parentheses, and then minus 1, close the parentheses. So I get 1.459. $1.4277. So here's the next one. And we'll do this. Okay. So there's that first one. There's the second one. It's getting it pretty quickly, right? Okay. And we'll just do 3. So we've got that one, and then this is 1.4277. 777. Maybe like 6 places. 1.427 7731 77315. So that's what we think it is. How could we find out for sure? You plug it in. Okay, put it in right here. So let's see what we get if we took, let's do 3 cosine of that last answer. And then let's subtract that last answer. And then let's add 1. Wow. If you had a graphing calculator, you could actually look at it and have it do the root finding capabilities on the calculator and find where it crosses. Okay? Any questions there? Okay. Not a good test question, but kind of interesting. Okay, this next one would be a good test question because it makes you think just a little bit, and it's very doable on a regular old calculator, and just kind of taking a guess as to what it would be. Roughly, what's the cube root of 28? Roughly 3. It's a little more than 3, right? Already got a guess. Okay, but in order to find another guess that's more accurate using Newton's method, you've got to have a function and you've got to have a derivative. Yeah.
But this is another one. Just be a
It is. So we got to be clever about this, okay? It's asking you to approximate the cube root of 28 using Newton's method. And Newton's method requires a guess, easy to find on this one, and it needs a function and a derivative. So what we're really asking here is, aren't we asking what number cubed gives us 28? That's the definition of the cube root of a number, right? What number do you cube to get that number? So this is asking this question. What number do you cube to get 28? That's the question. Now what do we do with this? Set it equal to 0. So here's our function. F of x equals x cubed minus 28. Here's our derivative, 3x squared. And what was x naught? What was our guess? Our guess was 3, okay? Now, this you can do by hand. So here's our first guess. Here's our next guess. Our next guess is going to be the old guess minus the function value at the old guess. So that's going to be 27 minus 28 over the derivative at the old guess. So the derivative at the old guess, 27. So this is going to be, now we said it was going to be a little bit more than 3, right? And look what happens here. This is going to be 3. This is negative 1 over 27. So minus a minus 1 over 27. This would be plus 1 over 27. So that means x1 is going to be, let's see if I got that in 27ths. That's going to be 81 27ths. So this is 82 27ths. Is that right? Okay, now we should be able to at least write down the next one. The next one's going to be 82 27ths minus the function value at that 82 27ths. So that's going to be 82 27ths. Be thankful you've got a calculator here. Over 3 times 82 27ths squared. Okay, let's have the calculator do the heavy lifting for us here. Clear this off. Our guess, plug that in, and then it's the same setup every time. The only thing is the structure of those functions has to change because the functions have changed. So this is going to be that last answer minus the function value at that last answer. So again, set of parentheses, and that function is, we're going to take the answer and we're going to cube it. Then we're going to subtract 28. That'll give us the function value at the old guess. Then we're going to divide that by the derivative, and that's 3, old guess, old answer squared, close the set of parentheses. And again, just for the heck of it, this usually does pretty well as long as the fractions aren't too ugly. There's our 82 27ths. I'm going to recall that again, because again, that's going to use my guess here. It's going to use that 82 27ths. It's recalled that as the last answer. It's going to plug that in there. And this ugly mess right here is that one right there. And take a look here, okay? Definitely accurate to the hundredths place just on the first iteration. The one that we could do by hand was accurate to the hundredths place. I mean, if you went back and told, a junior high teacher that you can approximate cube roots to the hundredths place relatively quickly, what's that? Without a calculator. That'd be kind of cool, okay? And all we need to do is just keep hitting enter and look at that. So this is first iteration, second iteration, third iteration, fourth iteration. Again, we're right on, okay? Let's see if it'll figure it out. If it's this long, now let's see, cube root of 28, rational or irrational? Irrational. It should struggle with this. It'll be interesting if it can do this. Nope. It'd be interesting at what level it can't do it. Okay. I mean, it's pretty good at making those transformations. But any questions there? Okay. Just as a point of interest, did anybody see, what do they call that? The Google Doodle? You know how they change the Google thing every day? Yesterday it was a woman who, I think she was 84 when she passed away. She was from India. She was known as the human calculator. She could do cube roots of ridiculously large numbers just like that. It's pretty interesting to watch. Okay, so let's talk about some of the pitfalls of this technique, because, I mean, it is pretty darn cool, but it does have its problems, just like any nice little shortcut or something like that. So here's the first problem we could have. So take a look at that first diagram there. What's the problem with trying to find this 0 right here using that point? Derivative is 0. Okay, now there are a couple things with that. What's the problem with the picture if the derivative is 0? If the slope is 0? Yeah, it's not angled. It's never going to cross the x-axis. So even if this was your guess, we end up with a horizontal line that's never going to cross the x-axis. Come back here and take a look at how Newton's method works. You've got the derivative in the denominator. If the derivative is 0 at that point, this falls apart. You don't get a next guess, okay? So you've got some issues either way. This is kind of unique. Take a look at this diagram and tell me what's happening here. Not a vertical tangent. Although that could be a problem. Take a look at what's happening. Can you identify where the first guess is? Where's our initial guess? Okay, it's right here. Okay, so what happens is we skip past the answer, and even worse, we come up here and we find the tangent line, and where does this shoot us back toward? Okay, right back to the first guess. So what will happen if we keep doing this over and over and over again? It's going to bounce back and forth. Okay, it's not going to find that one right there. Okay? So that can happen if we've got some symmetry around that 0. We'd have to be a little bit careful with that. And that does have to do with the vertical tangent. Not necessarily a point of inflection. It has to do with the shape on either side. It's got to be perfect. So the way to describe it is it's got rotational symmetry around that point. It's kind of odd around that point. Okay? Yeah. Yeah, it wouldn't. It depends. It depends on what the function was and what your guess was. It might find it sometimes. You've got to be careful if you've got a function where the derivative doesn't exist, okay, or where it equals 0. Okay. Okay. Here's another one. We're trying to find this one. So we guessed something that was nearby. Or sorry, we're trying to find this one over here. Guessed one that was relatively nearby, but it was past this little minimum value where the derivative equals 0. And what that does is it shoots us over here and finds this one right here. Okay? So if you've used a TI calculator before and its root finding capabilities, it asks you to give it a little window, and then it says, give me a guess. The reason it wants you to give it a guess is so that it finds the one that you want. Okay? You want to get close enough that it makes that root finding a little bit easier. Okay. This one's a little bit unusual. Here's the one we want to find. Guess one that's pretty nearby. Okay. That guess shoots it way over here. Why did it shoot way over there? It's the tangent line, but yeah. Shot it over to the left because it was on the left side of that maximum value. I'll take that. Pretty shallow line. So the smaller the derivative is, think about this. Think about where the derivative appears in the formula. It appears in the denominator, right? So the smaller the derivative is, the bigger the adjustment on your guess is going to be. Because you're dividing by something that's really small. So the smaller the derivative is, the further it's going to shoot away from the original guess, which sometimes can be a problem, sometimes not. The worst case would be this right here. That's as small as the derivative can get, 0, and then the method breaks down. Okay? So you want to be a little bit careful with those. Okay. If I give you one of these on a test, it's probably only going to have 1 0, and it'll be relatively easy to make a good guess to start with. Okay? Anything else there? Okay. So this one had 2 very nice answers. If we were going to solve this using Newton's method, we'd need a function, and what would that function be? X squared plus 3x plus 2. We've got to set it equal to 0. And then our derivative would be 2x plus 3. And then take a guess. You could guess 0. If you guess 0, which one's it probably going to find? It's probably going to find the negative one. Okay? All right. That's the whole idea. Again, if I give you one of these on a test, it's going to be one where it's relatively easy to make a guess. It wouldn't be a function like this guy right here, because that's not an easy one to make a guess, and it's not one that you can even do one iteration by hand. Okay? You could expect to see something like this, where you can at least come up with one decimal approximation, one fraction based on this method. Yeah. Mm-hmm. Yeah. I don't think many of them do. I think most of them only have one. Okay. Anything else? Okay. All right. That is it. If you've got questions and want to